Hello, I'm Anya Samadi. I'm working at Max Planck Institute for Solar System Research as a postdoctoral researcher, and I want to briefly talk about my research outlines in this through these slides. So I'm interested in studying the astrophysical processes in the stars that are residing in the binary system and also the results of their interactions. I normally use the a photometric light curve for this system, and I'm also check if the stars have any period variations that can be the result of a magnetic field, a spot activity, or the presence of a third body. I also do binary modeling, which is simply deriving the fundamental parameters, stellar atmosphere parameters, and also binary configuration of these of the stars, binary stars, in the case that they are eclipsing. But the main time of my research is past detecting the stellar pulsations in binary systems, the ones that have AF-type companions, and sometimes when both of the stars in the binary system are AF type, I also need to detect if both stars are pulsating, and if one of them have the delta Scuti pulsations, the other have the gamma Dor, or both of them have both type of the pulsations, or the reverse. Gamma Dor delta Scuti pulsators are the stars that, as you can see here in the pulsating HR diagram, they are located on the main sequence, but in the cross section of the main sequence and Cepheid instability strip. And you can see that they are located in a region that this region has some overlaps with each other. I also started to work on the ROAP stars, rotating AP stars and pulsating, but I will talk about only the Gamma Dor and delta Scuti stars. As you can see here, the main difference between Gamma Dor and delta Scuti pulsation is that the Gamma Dor stars are showing the gravity G modes that are having gravity as their resorting force, and they are coming from the close to the core regions, but the delta Scuti pulsations are high frequency pulsations, and the pulsations are excited, the modes are excited in the shallower and closer to the surface layers. Sometimes the studies show that most of the delta Scuti and Gamma Dor stars, many of the delta Scuti and Gamma Dor stars can have also intermediate to fast rotations. In these cases, if we are lucky, we can see, and these R modes are showing up in the Fourier spectrum, and also they are excited because of the rotation and can give us more information about the stars. Because of the overlap in these regions between Gamma Dor and delta Scuti pulsators, their studies show that most of the delta Scuti pulsators also are showing low frequency, low amplitude G modes, and it is the case for many of the Gamma Dor stars that have both the G modes and the P modes excited. So we are calling this type of the stars hybrid stars, and they are giving us the opportunity to study many layers of the star, starting from the ones close to the surface and going to deep interior of the stars, close to the core of the star. So from now on, I will call them the hybrid star, as it called in the astroseismology. I'm caring about the binary stars and the pulsations of the stars that are in the binary system, because the binary systems are very important. The main important thing about them is that we always, as astrophysicists, interested in deriving very precise mass for stars, because that is the parameter that can tell us about the evolution of the star and its structure. And so the binary systems, the eclipsing binary system and double line spectroscopic binary system, provide us easier access to calculate and the more precise, sometimes 1 to 2% precise mass for the stars, and when we have very good models, also stellar model codes, so we can be more sure about the radius and the masses that we derive, which is not that easy for the to derive for the single stars. When we are caring about the pulsations in the binary system, we need to keep in mind that there are other processes also going up because of the influence of the binarity on the pulsations. For example, we are expecting to see the tidally forced modes that are splitted with a spacing as large as the orbital frequency and its harmonics. And this provides a very good field for us, very good access to answer some of the questions that we don't know, they are not very clear for us, like the influence of the pulsation on the binarity on the pulsation, and the other processes that are going on in the binary system, and consequently their evolution. So the data that I'm using is the photometry data, light curves, as I told, and because of the nature of the pulsations in these type of the stars, this data that are very low amplitude, we need very high precision photometry data that we get it from the Kepler and test, that you can see, and a close view to one of the case studies, the light curve of one of the case studies that I have here. Our tool to study the stellar pulsation is the true Fourier transform. We convert this time series to the frequency regime, and to study the low frequency, we normally convert it to the frequencies to the period regime too. We use other type of the observations normally to have more information about the stellar parameters for the stars that we are going to detect the pulsations for them. I will talk about two case studies. The first case study here that I have chosen from my works is an Algol type eclipsing binary system, which has the hybrid pulsations. You can see from the light curve, Kepler light curve that I had for these 2 quarters, I understood that the quadrature phases, the maximum light in the quadrature phases of the binary system is variable, and you can see it here. And also the eclipse time variations for the secondary star is also varying. So these 3 gave me an information about the presence of a cyclic magnetic activity, long-term one, around 290 days. And I used 3 different binary models for 3 different phases. And then I could decode the spot evolution of the star, 2 stars, as you can see in different phases here, and how spots are evolving, merging, and shrinking. You can see here, and I could derive the stellar parameters for the star. From now on, I have some information to continue, and I have a model, binary model, that I know how much is the contribution of the light variations in the light curve because of the binary model. Normally, and this is the original light curve, and if you do Fourier transform, you have this Fourier spectrum up here, and you see these modes, these sequential modes, that they are just the harmonics of the orbital frequency. But if I subtract the binary model from this eclipse, from this original light curve, I came across to this very low level of the pulsation and low level of the light variations. And as you see here, compare these 2 with each other, that now we rarely see the orbitals, the harmonics of the orbital frequency, the G modes pulsations are showing up here with the low frequency lower than 5 per day. And then we also have these 2 bump up frequencies in the P mode region. So the star is a hybrid. And later on, according to the asymptotic theory of the pulsation, we expect that the G modes are appearing with the regular period spacing which I could detect them here, and I put them in the echelle diagram. They are located in a very good vertical reach, almost vertical reach, and in the period and in the frequency region for the higher frequency modes, I detected that all of these frequencies, most of them are spaced regularly with a spacing as large as orbital frequency. So these are tidally excited modes. So I could detect that the stellar parameters of the F-type star showing hybrid pulsations, they are coming from the F-type star, and we have no fast rotation, and also we have tidally excited P modes. The next step, which is very difficult for binary stars, is to compare the theoretically predicted modes with the modes that I detected. There is another study that has been done recently, and then to see how much these two are fitting with each other. The second case study that I want to show you as an example of the works that I'm doing is a double-line spectroscopic binary. It's again a Kepler target, and we have the full light curves for that. There is a pair, these are a pair of twin stars from the spectroscopy information that we have. The only difference between them is that one of them is a very fast rotator. This is V sin 962 kilometers per second, and the other one is a very slower rotator, not very slow rotator, and this is a long period binary. And then I first started from the high frequency region. You can see from 7 to 24.7.5 per day frequencies, and I could detect the two groups of frequencies. One group are splitted, having a frequency splitting with a different frequency, and the other one with another different frequency. If I consider some estimation of the radius, then I can say that each of these mode groups are coming from different, are showing us different rotational frequency, so and different rotational velocity, which is very close to the ones that spectroscopy says to us. So up to now, I know that both companions are pulsating, both have delta scuti pulsations, and also we can say that they are, both of them have these delta scutis, and I know which modes are coming from which star. And this forest of modes are the G mode region. You can see it's close to 0 to 7 per day, and we have different bump of frequencies, significant frequencies here, one here, and then the others, as I can show here. I could detect a frequency as large as one of those frequency spacing that I could detect it in the P mode region. So I understood, okay, this is the rotational frequency that I have detected. And the other thing, from the theory of the pulsations, I know that these Rossby waves that excited when we have the fast rotation, they are retrograde, okay? So their period spacing is increasing with period, and then they are located between m times of the rotational frequency. As you can see here, I'm showing 4 times of the rotational frequency, 3 times of the rotational frequency, and so on, but just in the period regime. So I detected this series of modes, both G modes and the P modes, and I could decode all of these frequencies one by one in the G mode region. So now that I studied both of the P modes and all of the frequencies also in the Fourier spectrum in the G modes, I could understand that one of the stars is a hybrid, and the other one is just the delta scuti pulsations, and I can say which modes are originating from which star. So this was an example of the works I'm doing. Please don't hesitate to send me emails in the case that you have any question.